everybody.
Today we are going to discuss a new kind of distribution out of that can be deduced out of joint bivariate distribution. This is known as conditional distributions. What is this conditional distribution? You see, we all know about conditional probability. What is conditional probability? The conditional probability. The definition of conditional probability was that if we have two events A and B, the probability of A given that the event B is already occurred, or simply we say probability of A given B, this is equal to probability of AB. This was the definition in terms of axiomatic sense. Probability of AB divided by probability of B, provided of course this probability of B is not equal to 0. That means B, this second event B, should be a possible event. It would not be an impossible event. If by chance B becomes is equal to an impossible event, in that case this definition is not true at all, or you can say in that case the definition of conditional probability does not exist. All right, so this idea of conditional probability exists only when probability of B is not equal to 0. Now with this same kind of idea, if we consider this event capital A, this event capital A as the event, we are first defining this one for discrete distributions, and similar definition will be discussed in case of continuous distribution. So in case of discrete distribution, at first if you consider this kind of event that capital X is equal to xi, if we define the event capital A in the fashion that capital X is equal to xi and B is the event that capital Y is equal to yj. Alright, in such cases you see A given B, probability of A given B, this can be written as probability that X is equal to xi, that is the event capital A, given Y is equal to yj, and that would be is equal to probability of AB. This is the probability that X is equal to xi and Y is equal to yj, divided by probability that Y is equal to yj, that is the event capital B. This is the event capital B, Y is equal to yj. Alright, and over here in the numerator, what is this probability? This probability is equal to Fij, that is the probability mass function at the point X is equal to xi and Y is equal to yj. Fij divided by what is this? This one would be actually equal to the marginal probability mass function. All right, this would be the probability mass function for out of this joint probability distribution. The probability mass function of the joint probability distribution, and this is the marginal probability mass function of the marginal distribution of Y. So Fij. Okay. Probability, this is the probability mass function of the two-dimensional distribution, and this is the probability mass function of the marginal distribution of Y. So this is the definition of probability X is equal to xi given Y is equal to yj. Now the question is that if we define this conditional probability in this fashion, does this satisfy all the axioms of probability? Answer is yes. You see, this is actually the ratio of two different probability mass function. We know that probability mass function always satisfies two criteria. The first criteria is that if Ij, this whatever be the joint or marginal distribution, all this should be greater than is equal to 0. And secondly, the summation If we have only single index, then we shall have single summation. If we have a double index, then we shall have double summation. Whatever it is, so summation over all possible indices of Fij, this should be is equal to 1. Alright. So now in this case also we need to verify whether this conditional probability defined in this fashion satisfies these two properties. And over here, this one, if ij divided by fyj, what is this? This is actually the conditional probability. So we shall designate this one by if I given j. All right, in this fashion, if I given j, if just computed at the point x is equal to xi, that's why we have I given, this is bar given j, that means y is equal to yj. This value is provided, maybe yj is equal to 1 or 2 or 3, it depends upon the problem. So we shall designate this one by if I given j. Now we are going to show that this satisfies this the properties of probability mass function. That means you see this is the ratio, therefore it is always greater than or equal to 0. And secondly, if we consider the summation on what you see over here, y is equal to yj, it is a given value. So yj is a fixed quantity. Only variable quantity is over here the index I. So over here the summation has to be taken on the index I. Here, so theoretically I is equal to minus infinity to infinity if I given j. So I think some kind of printing mistake or something is there. I given j should be written this way. I given j. Probability I given j is equal to if what is this probability of I given j? Let me show you over here. Probability of I given j. So what we have, if I given j, this is equal to if ij divided by if yj. So now if we choose the summation, this over here, say summation over I, theoretically I is equal to minus infinity to infinity, summation over I, if I given j. In that case, we should write it in this way, summation over I. I'm not writing repeatedly from minus infinity to infinity. So it is understood that I summation over I means I would vary from minus infinity to infinity. So summation over I if ij divided by if yj. Now you see this expression in the denominator, this expression does not depend upon this index I. It is actually dependent upon this index j, and j is over here a fixed index. Y is equal to yj is provided, so the value of this index j is fixed. So you can say this quantity does not depend upon I, and therefore this quantity can be taken outside the summation symbol. Therefore this can be written as 1 by y j, sorry, f yj, 1 by f yj, and that would be summation of f ij, summation over I. Now this expression inside bracket, if you recall the definition of f yj, the marginal probability mass function f yj, what was this? This was actually nothing but equal to the summation of Fij over the other index I. I is equal to minus infinity to infinity. Over here also we are taking I is equal to minus infinity to infinity. Got it? So this so from this definition of marginal density function, we can say that this expression inside this bracket, this is nothing but is equal to f y j. and we already have this 1 by fyj, so we can write this divided by fyj, and that is nothing but is equal to 1. Got. So in this way, we can say that the summation of all this type of quantity, if I given j, is equal to 1. And of course, this is greater than is equal to 0. Therefore, we have these two conditions: if I given j greater than is equal to 0, and its summation is equal to 1. Hmm. That means this if I given j satisfies the properties of probability mass function. And this if I given j, this is called the probability mass function, EMF, probability mass function of the conditional distribution. Conditional distribution of y. Conditional distribution of conditional distribution of x. Sorry, conditional distribution of x given y is equal to yj. Alright, given y is equal to yj. So this is the probability mass function of the conditional distribution of x given y is equal to yj, and this is defined as the ratio of fij divided by fyj. And in the similar fashion, we can define the conditional distribution of y. Okay, conditional distribution of y given x is equal to, maybe you can call it xi. So what would be actually the corresponding probability mass function? That should be written in this way: if j given I. And what is this? This is nothing but is equal to the probability that y is equal to yj given x is equal to xi, and that would be ultimately, by definition of this conditional probability, that would be is equal to fij divided by f what xi, the marginal distribution of x, because it is given x is equal to xi. It is given that x is equal to xi, therefore it should be divided by the marginal distribution of x. And this it can also be proved that this is greater than is equal to 0, and summation if j given I, j given I, over here summation should be taken on j, because I is equal to fixed, j is equal to minus infinity, and this value can also be proved to be equal to 1. So these are about conditional distribution in case of discrete distribution. The idea of conditional distributions in case of discrete distributions. Now, in case of continuous distribution, what would be the idea of conditional distribution? Now, the problem in case of continuous distribution is that we cannot simply write y is equal to maybe something like b. This event, the probability of this kind of event, or x is equal to a, the probability of this kind of event is always equal to b, is equal to 0. So if we define this event simply by capital B and this event simply by capital A, in that case we cannot define probability that A given B, because in this definition over here the probability of B in case of continuous distribution, the probability of this kind of point, probability of B becomes is equal to 0. Even probability of this kind of event capital A becomes also is equal to 0. Therefore, we cannot directly define this probability is equal to probability of AB divided by probability of B, because over here this probability is equal to 0, this denominator. So over here we need a little modification of the idea in case of continuous distribution. Okay. So in case of continuous distribution, how do we practically define the all these kind of conditional events? we actually define at first this y is equal to suppose b. We define this event y is equal to b in the sense of limit. We say that y is equal to b is actually is the limiting case of the event that b less than capital Y less than y sorry less than or is equal to b plus delta y. Let me make it a little concise over here. Say b less than capital Y less than is equal to b plus delta y. Or in your book you may have this type of idea. Over here, of course, delta y tending to 0. In the book, it is also written in this way that capital Y is equal to small y is defined in this way, that limit in place of b we are just putting small y. The small y less than or is equal less than strictly less than capital Y less than or is equal to small y plus delta y with the limit that delta y tending to 0. Okay, so this is the idea that we shall consider over here. At first, we shall prove this we shall try to compute this value probability that a less than x less than or is equal to say b given y less than capital Y less than or is equal to say y plus delta y. Okay, and by the application of mean value theorem and all, it can be proved that if we take the limit, if we take the limit as y tending delta y tending to 0, taking limit delta y tending to 0, but we shall write probability a less than capital X less than is equal to b, sorry, less than is equal to b given this is the event capital A. All right, this is the event capital A given y is equal to small y. That is equal to the limit of this event, limit of this expression with delta y tending to 0. And it can be proved that by the help of mean value theorem and after taking all such limits, I am not showing the intermediate calculations. It can be proved that this is equal to the ratio of two quantities. One is the integral from a to b f x comma y. Integration is taken on dx divided by the marginal density function of y. Alright, and you see this marginal density function of y, this denominator does not depend upon x. That's why this expression, this quantity can also be written in this way, from integration from a to b f x comma y divided by f y, marginal density function of y, integration taken over dx. And now this expression inside this integral symbol, this expression, if we now suppose that this expression, the integral, this integrand, if we consider this integrand f of x comma y divided by f y. If we assume this integrand and write it in this way, if x given y, it is, let me write it over here. If we write this one as a x given y, and over here y is actually a function. Y is actually small y is actually a parameter, not function. Y is actually a parameter, so this is actually a function of x. That's why we write it as suffix in order to designate that this is actually a function of x. F suffix x of x given y. And in that case, this integral can be written as integral from a to b fx x given y dx. All right, and it can be shown that this expression, this one, by this right hand side expression, satisfies all the properties of probability density function, and this one is called the probability density function of the conditional distribution of x given y is equal to small y. So y is equal to small y is always meant in this kind of limiting sense. Y is equal to small y always means in this kind of limiting sense. Okay, mind keep this one in your mind, that y is equal to small y is always defined in this kind of limiting sense. So over here we got the conditional density function of x. So let me summarize this one in the next page. So we have the conditional density function of x as fx x given y. Over here, mind it, y is parameter. Y is, it behaves like a parameter. As you see, we already have different kind of distributions or different kind of density functions. Say for example, in binomial density binomial distribution, we have two parameters p and n. N and p, these were two parameters in case of binomial distributions. In case of Poisson distribution, we had a parameter mu. In case of normal distribution for of one dimension, we had two parameters n and sigma. So likewise, over here, this quantity y behaves like a parameter of the distribution, and over here x is the variable. X is the variable, or you can say that variable, or you can say this is the is equal to the value of the random variable x. Value of the random variable of the random variable capital X. Okay. So in this way, we define the conditional distribution of x given y is equal to small y. Similarly, we can define the conditional distribution of y given x is equal to small x, and we shall designate it in this way. So what is this? This should be defined by the same technique, like say if x y divided by the marginal distribution of x. So if x x, what this next definition was, if xy divided by if y y, if y y. So over here you can see we get a rule that f of x comma y is equal to the marginal density function f y y multiplied by this conditional density function fx of x given y. And from this relation we obtain another expression of this fxy. So from this expression we can say that this x comma y will have this second expression that can also be written as fx x into fy of y given x. All right. So we can say that in general that this joint density function will be the product of a marginal density function along with the conditional density function of the other variable. Over here, the marginal density function of y multiplied by the conditional density function of x, and over here the marginal density function of x multiplied by the conditional density function of y. And we can observe that in case of this is a particular case, we can observe that in case of independent, I told you in the last class, in case of independent random variables, if the random variables are independent in that particular special case, what was the definition that we could deduce this result, that fxy is equal to fxx, the marginal density function of x, and fyy. Okay, so we can compare these two expressions, this expression along with this product and this product. So you can see that if you compare this product as this first line, okay, in that case you will identify that this conditional density function of x will become is equal to the marginal density function of x. Got it? And therefore, particularly only when it is independent, only when it is independent, we can say it means that in case of independent distributions or independent random variables, we can say that this marginal distribution fx x given y will become is equal to the this conditional distribution fx x given y will become is equal to the marginal distribution of x. Similarly, the conditional density function of y given x will become is equal to f y y. So initially it may appear that the notation of this kind of functions are a bit complicated. Then once we write a suffix and then x given y, but by practice I think this kind of complication will become solved for you. And this is the case only for independent random variables. Only when random variables are independent, then only we have this type of result. Otherwise, in general, we have these two relations that should be followed everywhere. And it can also be proved that whatever marginal density function you consider or whatever conditional density function you consider, you will always say in case of say this kind of density function fx x given y, the conditional density function of y, what was the definition? The definition of was that fxy divided by fyy. You can check that this is greater than is equal to 0. And now if we take the integration from a to b of this kind of expression fx x given y, this marginal density function, and if you integrate it with respect to x, we check, you can see that that would be is equal to integral from a to b, not a to b, rather let's write it as minus infinity to infinity in case of a to b. In case of this a to b, like that. Rather, we consider this limits as minus infinity to infinity. Over here, minus infinity to infinity. So we shall have fxy divided by fyy dx. And you see this quantity does not depend upon x, so we can take it outside the integral sign. We can shift it over here. We can shift this. We can shift this total entire quantity. We can write it this expression as equal to 1 by fy of y, integral from minus infinity to infinity f xy dx. And this expression within bracket, this is nothing but is equal to the marginal density function of y. So we can write this quantity as the numerator. We have fyy divided by again FY1. This expression within bracket is nothing but is equal to the marginal density function FY. Right? So this value of the integral is always equal to 1 over here. So you can check that this marginal, this conditional density functions also satisfy the relations that this is greater than is equal to 0, and integral of this kind of conditional density function over the interval minus infinity to infinity is equal to 1. So this kind of conditions are also satisfied if you consider the conditional density function of y given x. All right. These are this type of results can be considered or can be selected in exam for objective questions like a question of 2 marks. All right. So over here, let's discuss one or two examples. I discussed this kind of examples in our previous classes. Let's go through this book. I think in that case, I don't have to write all this in the board. Let's consider an example. You see, we considered this example earlier in the previous classes. In this example, I'm not discussing the entire detail of this example. The fact was that we had 9 points, and for x is equal to 0, this is the line. For x is equal to 0, we had y is equal to 0, this is 1 point. This is y is equal to, this is 1 point, y is equal to 1, then y is equal to 2, and then y is equal to 3. Next, for x is equal to 1, we had y is equal to 0, then y is equal to 1, and y is equal to 2. And for x is equal to 2, we had y is equal to 1, and y is equal to 2. So at this 9 points, 4 plus 3 plus 2, that is 9 points, the value of the density functions y is equal to 1 by 9. And otherwise, at these points, the probability was equal to probability was equal to 0. Therefore, the value of the density function was equal to 0. So now we proved in this case that capital X and capital Y, these two random variables, are not independent random variables. They were dependent on each other. We proved all these results, and now in this case we are trying to find out the conditional density functions. Okay, in this case we are going to find out the conditional density functions. So how to find out the conditional density functions? You see, we shall have to find out if I given j. I am over here going to discuss only one case, if ij. Suppose you can similarly find if j given I. So I am just going to discuss one conditional distribution f yj. Now, what is the value of j? J, the possible values of j are j is equal to 0, j is equal to 1, j is equal to 2, and j is equal to 3. These are the 4 possible values of j. Now, for example, particularly we consider j is equal to 0 for the first case. J is equal to 0. In that case, we shall have to find out if I given j, and for j is equal to 0, you can also write it as I given 0. Alright, now for j is equal to 0, the possible values of I for j is equal to 0. Oh, sorry, I made a mistake. I am very sorry. I made a mistake. For j is equal to 0, j is equal to 0 means this one. This line j is equal to 0 refers to this line, this one, the x-axis. J is equal to 0. Over here, j is equal to 1, then j is equal to 2, then j is equal to 3. So j is equal to 0 refers to this line, and what are the possible values of I for j is equal to 0? These are the 3 possible values of I. I is equal to 0, then I is equal to 1, and I is equal to 2. Okay. Now for j is equal to 0, we shall have to find if I given 0. So comma, you can take I is equal to at first 0 and then 1 and then 2. So these are the possible three values. So we shall have to write comma I is equal to 1. We shall have to compute for I is equal to 2 and then sorry, I is equal to 0, 1, 2. Not 1. It should start from 0 and then 1 and then 2. These are the three possible values of I. Okay. So let's try to find out for I is equal to 0, what is the value for I is equal to 0. That means 0 given 0. For j is equal to 0, it should be 0 given 0. So we need to compute 0, f of 0 given 0. How to compute f of 0 given 0? You see, f of 0 given 0, let me write it over here. F of 0 given 0. It means that as per the definition, if ij or over here I is equal to 0, j is equal to 0. So we should write f00 divided by fy0. fy0. So let's check what is fy0. You can see we already discussed fy0. This is fy0. You can see fy0 is equal to 1 by 3. Therefore, in case of fy0, we have fy0 fy0 is equal to 1 by 3. Now, what is f of 0, 0? At this point, f of 0, 0, f of 0, 0 is equal to 1 by 9. It is written that f of 0, 0 is equal to 1 by 9. So we should write 1 by 9 divided by 1 by 3. Therefore, it would be is equal to, simply after computation, this would be is equal to 1 by 3. So in this way, we compute f of 0 given 0. Alright. Now, what would be f of, we need to compute for I is equal to 1. So we shall have to compute f of 1, this kind of 1 given 0. Alright, now f1 given 0. What is f1 given 0? You see, f1 given 0, f1 given 0, that would be is equal to f10 divided by fy0. Now, what is f10? You see, at the point x is equal to 1 and y is equal to 0. This is the point, x is equal to 1, y is equal to 0. The value of f10 is again over here 1 by 9. So you can say that this value would again be is equal to 1 by 9 divided by 1 by 3. That is equal to again 1 by 3. Similarly, we can compute that if 2 given 0, that is also is equal to 1 by 3. So what we got is that for I is equal to 0, we have 1 by 3. For I is equal to 1, we have 1 by 3. For I is equal to 2, we have 1 by 3. So if we summarize these three results, we can simply say that if I given 0 is equal to 1 by 3, for I is equal to 0, then 1 and then 2. Okay, so in this way we got the marginal, we got the conditional density function when j is equal to 0. We got the conditional density function of x when j is equal to 0, or you can say y is equal to y. Similarly, we shall have to find the conditional density functions of x when j is equal to 1. So in that case, we shall have to write if I given 1 for different values of I. Again, we shall have to find if I given 2 when j is equal to 2, and if I given j is equal to 3, because you see over here four possible values of j are there. J is equal to 0, j is equal to 1, then j is equal to 2, and then j is equal to 3. So for all these 4 values of j, we can find conditional mass function or conditional distributions of x. So these are about conditional distributions of x. And in the second phase, you can also find out the conditional density, conditional mass function for y. So j given I, and I am leaving these remaining computations for you. All right. Hopefully, you can go through this problem, and if you have any problem in future about this type of questions, you can consult me in the subsequent classes. So this is all about the conditional mass function, or you can say the probability mass function for the conditional distribution of x and y. So this is an example in case of discrete distribution. And in case of continuous distribution also, we discussed one example. Probably this one. We discussed an example where we had to find out this kind of value of k. We found that the value of k is equal to probably 6. Yes, we got the result that value of k is equal to 6, and from this result we computed the marginal this marginal density functions of x and the marginal density functions of y. But in case of this, in case of continuous distribution, the computational process becomes a little bit easier. For example, you see, if you need to compute the marginal density function of x, then what to do? Fx x given y. Then what to do? You just compute the ratio f x comma y divided by f y of y. So that would be is equal to, you see, fx comma y. What is fx comma y? This is the fx comma y in the spectrum. K is equal to 6, so therefore 6 multiplied by 1 minus x minus y. This is the corresponding density function. Therefore over here we shall have 6 into 1 minus x minus y divided by, what is fyy? This is our fyy. 3 into 1 minus y square. 3 into 1 minus y square. 1 minus y whole square. 1 minus y whole square. Okay. So that would be is equal to 2 into 1 minus x minus y divided by 1 minus y whole square. But over here, what is the value or what is the range of y? What are the possible range of y in case of marginal, in case of conditional distribution? In case of marginal distribution, we do not have any problem. But in case of conditional distribution, you have to be a little bit conscious. You see, what is the spectrum? This is the spectrum. X greater than 0, y greater than 0, and x plus y less than 1. The picture probably is not given in this book. Let me draw the picture over here. You see, what we have? We have this type of coordinate axis, and on this kind of coordinate axis, what was the range? X greater than 0, y greater than 0, and x plus y less than 1. So x plus y less than 1 refers to this kind of straight line, where this is actually 1 unit of intercept, this is 1 unit of intercept. This is our x-axis, this is our y-axis. So this is the region on which these three inequalities will be satisfied. Okay. Now in this region, we need to identify the range of y. We already got the probability mass, the probability density function of x. If x given, f of x given y, like this, and what we got, this expression was equal to 2 into 1 minus x minus y, 2 into 1 minus x minus y divided by how much? 1 minus y whole square. So 1 minus y whole square. And you see, in any distribution, if we have a parameter over here, this is a probability distribution of the this is the probability density function of the conditional distribution of x. So y would behave like a parameter. Then what is the range of y? You need to identify the range of y. Now, in order to identify the range of y, what we need to do, we just draw a straight line parallel to y-axis. Okay, draw a straight line parallel to y-axis and try to identify the boundaries at which this straight line intersects. These are the two boundaries. You can say that this is one boundary line and this is another boundary line. And what is this equation? The equation of this lower boundary line is actually x-axis. And what is the equation of this x-axis? Y is equal to 0. And this is the upper boundary line. So what is the equation of this upper boundary line? The equation of this straight line is x plus y is equal to 1. Got it? So y should be written over here, y is equal to 1 minus x. And over here in this zone, y would vary from 0 to 1 minus x. Clear? That's why over here you need to particularly mention the value of the parameter, or the range of the parameter. Over here, y would vary from 0 to 1 minus x. The lower value is the lower limit of y is equal to 0. The upper limit of y is equal to 1 minus x. Therefore, you should write 0 less than y less than 1 minus x. And outside this zone, this is the zone of the parameter. And what is the spectrum of the variable x? Of course, x independently varying from 0 to 1. Over here you can see that this is the point 0 comma 0. So x is equal to 0, and the maximum possible value of x is this is the value 1 comma 0. So we can say that 0 less than x less than 1. Okay, so this inequality refers to the spectrum, and this inequality refers to the range of the parameter y. Therefore, if you need to write this density density function of the conditional distribution, you should need to write it in this way: if x comma y, this is equal to 2 into 1 minus x minus y divided by 1 minus y whole square, where these relations are satisfied, and 0 elsewhere. You generally make this mistake that you always forget to write this part, 0 elsewhere. Don't forget this portion. This is an important part. Okay, so this is the part where we have the spectrum, that within this spectrum 0 less than x less than 1, we get this kind of density. We get this kind of density function of the marginal distribution of y. So it should be given a comma. We should write given y. of x given y. Okay, so similar fashion, in the similar fashion, you can also find fy of y given x. So these were two examples. Now, in case of bivariate normal distribution, that is the main part I should discuss over here. In case of bivariate normal distribution, I am discussing this one from this computation. Already computation is done. Sometimes we need to find out the conditional density functions from a bivariate normal distribution. You see, this is the density function of the joint bivariate, the joint of this joint distribution of x and y. X and y is a bivariate normal distribution, and we already proved these results in the previous class, that this is the marginal density function of x and this is the marginal density function of y. Now, in order to find out this conditional density function of x given y, what we need to do? We need to just divide this quantity. This is the joint density function f of x comma y divided by the marginal density function f y of y. So just put this expression. This is the expression of joint density function, and this is the expression of marginal density function of y. Now, in order to make this computation little precise, we consider x minus mx by sigma x. Let us consider this one by x prime. I already discussed this computation of marginal distribution. We took x prime is equal to x minus mx divided by sigma x, and similarly we choose y minus my by sigma y is equal to y prime. In that case, this exponent that arises in case of bivariate normal distribution, this exponent can be written in brief as this type of result: y prime square into 1 minus rho square plus x prime minus rho y prime square. All right, and over here we are using the same result over here. You see this exponent. Let me make it a little larger. This exponent in the numerator can now be written in this fashion. Okay, this e to the power of minus 1 by 2 rho square into this y prime square into 1 minus rho square plus x prime minus rho y prime square, y prime whole square. And this expression of marginal density function, in this expression y minus my by sigma y can be written as e to the power of minus 1 by 2 y prime square. And now we are trying to decompose this expression in the numerator. You see this exponent, this e to the power of this kind of complicated exponent, this can be, if we decompose this one by distributive law, if this 1 minus rho square and this 1 minus rho square will get cancelled, so we shall have e to the power of minus half y prime square, and that would get cancelled with this expression in the denominator, and therefore only in the numerator we shall have the contribution coming out of this term y prime, x prime minus rho y prime whole square, and that would be multiplied by minus 1 by 2 into 1 minus rho square. So we shall have this type of exponent. This is an exponent, and this can be written elaborately, like if we write x prime is equal to x minus mx divided by sigma x, and y prime is equal to y minus my divided by sigma y, something like that. So this would be the density function of the conditional distribution of x given y is equal to small y in case of bivariate normal distribution. And similarly, we can also compute the conditional density function of y given capital X is equal to small x in this fashion. I am leaving this computation for your homework. Okay, so this much I wanted to discuss, and in the next class we will show out of this expression that by certain technique that is called the transformation process, we can find two independent standard normal variates out of this bivariate normal distribution, and this standard normal variates would be independent of each other. Okay, and that's in that kind of computation, all these steps would be very much important. In fact, all these results would be very much important. So please, in your home, you please do all these computations by your hand. This would be very much helpful for your future upcoming classes. So that's all for this lecture. Thank you for being with us.